Hi, welcome to the channel. Today let's try solving the lead code 1235 maximum profit in job scheduling. So first try reading the problem and then we'll see how to go uh, into the solution. Uh, okay, so let me read the problem and understand what is it asking. Uh, so let's say, okay, so we have n jobs where every job is scheduled to be done from the start time and end time, obtaining a profit of the profit I. Okay, so we are given the start time, end time, and profit arrays. Uh, I think our job is to return the maximum profit we can make out of scheduling these jobs. And there is a key detail here, that is there shouldn't be any two jobs in the subset with overlapping time range. Okay, so this means that no two jobs should have an overlapping time range. Let's write that here. No two jobs should have an overlapping time range. Okay, and it says if you choose a job that ends at time x, you will be able to start another job that starts at time x. Okay, let me read that again. So it says if you choose a job that ends at time x, you will be able to start another job that starts at time x. Okay. Okay, so let's see. I think this is a correct example for this is an important detail that should be kept in our minds. Okay, so all it's saying is that we have a job here that's starting at 1 and ending at 3, and there is no restriction that we shouldn't schedule this job which starts at 3 and ends at 6. So yeah. Okay, now so let's take an example and see if we can try to solve this problem and try to get some intuition into this. So let's take this example. So you have start and end time and profit. Uh, so yeah, so the goal is to see if this problem has a substructure in it. So I mean, what I mean to say is, so we have a set of jobs given and we are asked to calculate the maximum profit, but let's say we're only concerned with the last job. uh, so here the last job is starts at 3 and ends at 6 with a maximum profit of 70. So now so either, like, either we can choose to schedule this or we can not choose to schedule this. So we have two choices, which is either pick this job or not not pick this job. So what happens if we pick this job, right? So let's say if we choose to pick this job to schedule, uh, what is the profit of this? It is 70. So we are talking about this job here, which starts at 3 and ends at 6. So we have 70 here, and we also need the profit that we made um, at the before this job starts, like that is at the time 3. So we need the max profit at times 3, just on a high level, so which is how we get 70 plus 50, that is equals to 120, right? So just on a high level, this would be the solution for this problem. uh no What did we just do here? So So this is for picking the job. So if we pick the job, we have the value as 120. What if we don't pick the job, right? So if we do not pick the job, then we, let's say, not picking the job, right? So if we do not pick the job, then what we are essentially saying is we will not be using this profit of 70, and we're just saying I'm okay with whatever the profit that was made earlier, right? So just use the earlier profit that we don't know whatever it is. Okay, but in this case, let's see. So this job is ending at 6. So what is the job that is ending before 6, right? So it's 5. So what is the profit that was made at 5, right? So that is the answer to this problem. Let's say let's just say like f of 5. Okay, so this is a recursive problem, but essentially that's what we are doing here. So we have two choices. uh, so the our initial goal was to, we're just concerned with picking this last job or not, to calculate our overall maximum profit from the given set of jobs. So if we either, we can either pick the job or not pick the job. So if we pick the job, then we need the current profit of the profit of the job, and also the maximum profit that was made at time 3, which is nothing but the start time of this job. Like what is the maximum profit at time 3? Like, just say this as f of 3 for now. So that is 50 from this diagram which we see here. So it's 120. So we have two choices, right? So this, the profit that was made if we pick the job is 120, and the profit that was made if we not pick the job is f of 5. And f of 5, if we can just calculate from this solution, which is so maximum profit at f at n time 5 is 50 plus 40 is 90. So it's clear. So we have to choose 120 over 90. We just have to choose the maximum profit. So it would be 120. Okay, so we just, and that is our final solution here, right? So we can conclude that there is a substructure to this problem. Either, so we're still not 100% sure of how to calculate the maximum profit at, the earlier times. So here we did directly substituted 50 here and 90 here, but we didn't exactly calculate how. But you can see that there is a substructure to this problem. So just to make it even more clearer, let me write the a simple equation sort of it. So let's say max profit at job I is nothing but just the max of profit at job I plus the best profit before the job starts. Okay, and we are also, that is one of the choice, which is picking the job, and the second choice is not picking the job, which is best profit before this job ends. So yeah, these are the two choices which we have listed down here. So let's look at the one of the approach to solve this problem. um, So let's see what if, since we have established that there is a substructure here, and obviously there is also an optimal substructure, like there are overlapping problems as well. Because if you see, let's say for example, let's say there are multiple jobs uh, starting at 3. Like if you see for example here, there is this job starting at 3, from 3 and ending at 5, and 3 and ending at 6. So you will have the overlapping subproblems, because when you're calculating the maximum profit for the job 3 to 5, you are going to calculate the, you will need the answer for f of 3. And again, when you are calculating the profit for 3 to 6, you again end up calculating for f of 3 again. So which is nothing but there are overlapping subproblems, which means you can solve this using the DP approach, preferably bottom up. uh, so one of the approach I could think of is, this is just initial intuition of the bottom up DP approach. So what if we, again, I don't know if this would be an optimal solution, but I just wanted to just see how the this initial intuition goes. So let's say if we have let's say we have if we build a grid, the classic way of solving the DP problems, which is, uh, let's say if you build a grid with all the start times and the end times, that is the rows as the maximum start time, and the columns with the maximum end time. So I just thought of doing this and see where it goes. So let's see, if you have the maximum time, start time is 3 and the end time is 6. So let's see if we build this grid and we sort of supply the values or place these values in the relevant grids. And by applying this equation here, uh, if you see here, all this would be, in some of the base cases would be, if the start time is greater than the end time, then fill zeros in those cells. uh, then, so when it comes to this one, so we have, when we try to solve this problem here, which is table of, let's say I'm calling this table of 1 3. So what does the value here represents? I think so the value here represents the maximum profit uh, until the end time for a particular, actually, maximum profit possible, maximum profit until, for a given start and end time. So that would be the, that is what the value, uh, each cell value represents the maximum profit for a given start and end time. So all the base case would be 0, because there is no job with start time 0, and same thing with fill in the zeros that satisfy this condition. And yeah, so when we come to this cell, so there is a job that starts with time 1 and end with 3. So for that, there is profit is 50, and we just fill it with 50. And when we come to this cell, which has the start time 2 and end time 3, but there is no job with the start time 2 and end time 3, we only fill with the previous max profit, which is 50. Same thing with this cell. There's no job with start time 3 and end time 3. So we just fill it with 50 again. Same thing with the rest of the same thing with 3 comma 4 as well. But when we come to here, it's 2 comma 4. So there is a job with start time 2 and end time 4, and the profit is 10, right? So what do we do here? So as I said, we have two choices. We either schedule the job or we do not schedule the job. So if we choose to schedule the job, the profit is 10. So the our equation here is, if we choose to schedule the job, it is 10 plus best profit before the job starts. So the best profit before the job starts is the profit at time 2. So what is the profit at time 2? It is 0. So it is either 10 or the previous one. So the previous end time has 50. So max of 10 comma 50 is 50. So we do the same thing here for the rest of the cells. So we do not have the jobs for this cell and this cell. Again, when we come here, we do have a job that is starting at 3 and 5, ending at 5. So if you apply the same thing, we will have either 50 comma 90. We choose the maximum and we fill it with 90, and we do the same thing here. uh, there is no job with that starts at 3 and ends at 6. So the only option, if we do not have the job, is to choose the previous max. So the previous max, we calculate it by calculating the maximum of this column. As I said, this column represents the end time. So we need so our equation states that if there is no job, we decide to fill the max at the previous end time, right? So the previous end time here is 90, so we just fill it with 90. The same thing here, we do not have the job with 2 comma 6, so we fill it with the previous max, which is 90. Yeah, so when we come to the last job, which is 3 and 6, so we do have 3 and 6. uh, so if we decide to schedule it, it would be 50 plus 70. So 50. So what is the maximum profit at the end time 3? It is 50. So if we decide 50 plus 70, it's 120. So it's either, if you do not schedule the job, it's 90. If you schedule the job, it's 120. So it's definitely, we choose 120 because our equation states that we have to choose the max of both the choices. So yeah, so this would be the final result would be table of -1 comma -1, or the, yeah, so this would give the result of the final answer, because that is the 3 comma 6 is the last job, and that's the value at that is 120. So this works, but let's see what are the downsides of this solution. So one initial downsides of this is the space complexity. So if you see, the space complexity will be very high, because the rows and columns, we are creating a grid of, that is of complexity max O of max, uh, max start time and end time, which is really bad, uh, because let's say if you're, and if you look at the constraints here, okay, so the end time, okay, so the end time is, can take the values from 1 to 10 to the power of 9, which is really huge. um, yeah, same thing with the max start time. So this grid could grow from like really huge. And for example, let's say if you are and let's say if the value is 10 to the power of 9, either start or end time, then this could be really huge and we are going to get the memory issues. So, and what about the time complexity here? Again, the time complexity is, again, the max, is the same thing as its max start time in and max end time. So, and and if you just take a look, the reason why I highlighted these, this red blocks and the green block. So the green block is a solution, but if you see, our result is just like slightly only dependent on the red blocks. Like all these, the cells which are not highlighted, we are actually not using those. So which means we are calculating or solving the sub problems which we don't need. For example, right, so let's take this cell which is 3 comma 4. So there's no job with the start and end times, but we're still calculating it, which which is not, which is like an overkill for this problem. uh, Now this grid will be useful if the problem would have asked, like, like if the problem would be, like if the user wants, like if you think this as some scheduler that some service is using, some user wants to know, like he or she wants to query what is the maximum profit for a given start and end times, right? Then I think this grid would be useful in that scenario. Like for example, if I wanted to know what is the maximum profit at 1 comma 4, then I can just directly look it up, which is 50. What is the maximum profit at 2 comma 5? It's 50. Same thing with whatever, irrespective of the job scheduled or not, irrespective of if there is a job with those start and end times. So in that scenario, this grid would be really useful. But for this problem, I'm not sure if we really need this grid. And considering the space and time complexity, which is which can be deterrent to this solution. Uh, and if you see, we are only concerned with the end times here. So all we are looking for is what is the maximum profit at a particular endpoint. So we're not even looking for the start time. Just the end time is enough. Let's say for example, while filling this cell, So what we are asking is, so there is no job that is scheduled at 3 comma 6 start and end times, but what is the maximum profit at 5, right? So we're just targeting the end times, not even the start times. So we can convert this 2D approach into a 1D. So let's see, let me write it down here. So our first approach is a 2D approach where the problem is the memory and the space complexity, and the space and time complexity are huge. The second approach, which I think we could still solve, is using a 1D, where the 1D array, where the array ranges from 1 to max n time. So we can still solve this, we can optimize this solution. So instead of creating a 2D table with start and end times, we can just create a 1D with maximum end time, with the range of 0 to maximum end time. So we can still use the same logic here that we have applied for 2D and apply for the 1D, but still the problem exists. uh, the space complexity could be like 0 to the max end time, and the max end time, as we saw here, it's 10.9. We might still face uh, the memory issues if we use this solution. um, Now, is there a third approach? So let's say, think about the third approach. So I think earlier, one and two, we were more focused in finding the maximum profit at a given end time. Because if you see in the first table, we were more focused to have the profit at any given start and end time. And in the second approach, we reduced that to a 1D array of all the maximum end times. And still, there it was all about having the maximum profit at each endpoint. So, and we found out that the space complexity is one of the major issue in both, and the time complexity as well in the first one, because in the first one it is almost O of n square. So what I was thinking is, instead of having the maximum profit at every end time, what if we say, uh, let's say if we are coming back to the initial question, initial thought process, like, what if we are only tasked to schedule, to calculate the profit, to schedule the last job, which is 3 comma 6, right? um, so what you're trying to say is, so maximum profit at job I equals to, the two choices here are the maximum profit at job I plus the best profit before the job ends. Now, the best profit before the job starts, right? So this is what, the reason which we have gone to this 1 and 2 is because to find the values of these, the best profit before the job starts. Here in this case it's 3, the profit at 3, best profit before this job ends, which means the 5. So which is why we have opted for the 1 and 2 approach. But can we say like best profit after scheduling the first, the I minus 1 jobs, right? So instead of, let's say, I can just put max profit at job I plus, so it says best profit before the job starts, right? It's somewhere, it's this 3. So what we are asking is, first of all, what is the job that is ending before the start time, and what is the profit at that point? So it's like saying job that has, so f of job id, let's say I'm just calling the id job of f of job id. The job id here is the job that is ending, that has the end time less than or equal to 3, right? Comma, best profit before the job ends. So this job 3 comma 6 is ending at 6. So it's like saying what is the profit of the earlier 3 jobs. It's like saying f of I minus 1. Yeah, so you have two choices here. This is one choice. This is the skipping the current job, choosing the current job. So this job id we have to find. So this I'm just writing it down. So the job id is the job ending, the job with the end time less than or equal to start time of the current job. Yeah, so now it's clear. So we can have a jobs uh, array with the length of the maximum jobs, and we can try building the solution from the solutions for all the sub problems, and then finally have the answer. And I just had a, so the job table, the TP table would be something like this. So you have the job 1, it's 50, and job 2, which is again 50, 3, job 3, the maximum profit after for scheduling. So here DPI is maximum profit after scheduling I jobs. That's the key distinction here. Maximum profit after scheduling I jobs. Earlier it was maximum profit until a particular end time. So earlier two approaches were mostly time specific. Here it was job specific. So the time complexity here would be, I think it would be linear time, and space complexity, which was a downside in the earlier two approaches, is very much, it's like O of number of jobs. There's no more end time bound for the space complexity. So I just wanted to share some of the observations of these three approaches. I think the first approach which we calculated here, right? This would be more suitable, let's say if you're building a distributed system or any large scale system, and there is some job scheduler that wanted some like wanted to know what is the max, wanted to query the profits. Let's say there are some hundred set of jobs that are that has to be scheduled or already scheduled, and we build this table. And if the use case is like, let's say I wanted to know the maximum profit at any particular start and end time, then the your service can just come and look up these values. So that would be a better so this would be a better solution for that use case, like for querying the profits for any given start and end times, right? And that would be one scenario where this table could be useful. And the second scenario would be, let's say if we have a dynamic way of updating the jobs, like adding the jobs to the queue. Let's say if there is a new job has to be scheduled at with start time 1 comma 4, and you wanted to know what is the current maximum profit, right? Then, and the new profit, a new job's profit is, let's say, 100. So you somehow just can just come here and update the value here, and just, yeah, you have to update the other cells as well. So I think this would be better solution for those scenarios, not for the current, for this problem. I think this would be a really overkill. And as we have already discussed, the space complexity and time complexity are also huge for this approach. Same with the second one. The second one, we're just removing the start times and making it a single one dimensional array with a maximum time. Same with this, there would be other scenarios, but it's not the right solution for this problem. For this problem, I think the correct optimized solution is this one. Uh, yeah, so here, so the linear time would be for actually, you know what? It's not linear time. So it would be linear time for updating the table, but for to update the table, there is a so you still need to know uh, the job ID, right? So for this operation, uh, it would take log n, because what we're essentially asking here is to find the job ID. Like here, so we are asking for the job ID which has the end time less than or equal to start. So that means uh, we are we can either do a linear search there, or we can also do a binary search on on a sorted times, sorted jobs. So which would be, a binary search is a log n, so it would be O of n log n. So there's a huge step up uh, from the earlier use cases, like O of n square here, and here it's same thing. Yeah. So So let's try to code the solution for the third approach, which we have finally decided. So first thing is we have to sort the jobs. So sort the given jobs. So um, so let's try to zip to make sure zip let's say start time comma end time profit. Just trying to zip and making a single object. Sorting sorted profit, okay. Key is equals to lambda x of x1 and let's also create an end. Let's see, so just getting a length of jobs, and the dp table will be of size n+1. So just for our reference, dpi here is the max profit using the jobs from 0 to I. So at dp of 0 it would be 0. Yeah. Now let's try to iterate the table. So for I in range of 1 comma n+1, so you have a start, so jobs of I minus 1, because we need the, so this is essentially the start comma end comma profit of the current job which we are calculating the profit for. So jobs I minus 1 equals to, let's say, s comma e comma p. I'm just unpacking the, and then now we have two choices here, either to include it or skip it. So we need the values for both the choices. First, let's say we include the profit, that is equals to, so for the inclusion of it, this is the solution, this is what we have to calculate. So what is a profit? Profit is already there, which is sp, and we need now we need the job id, right? So we need the job id that is ending, that has the end time that is less than or equal to the start time. So for that I think we need to do a binary search, right? So let's put it here. So job underscore id is equals to binary underscore search. So for this we needed to do the jobs, and the target, the start time is the target. So this should give us the job id, the target job id that we are looking for. And now, which is the dp of job underscore id, I think this is should be fine. Now let's say the other choice, which is skip the job and get the max profit. So this would be Let's see. uh, yeah, so this would be skip underscore profit is equals to, I think this would just be directly, it would be I, because it should be, mm, yeah, it should be I minus 1. Yes, it should be I minus 1. And then okay, we can just directly return the dp of I minus dp of the last row. But first we have, for that we need to update it. So dp of I equals to max of include and skip. So I think this should be, and also we need, okay, and we would also need to implement the binary search here. Binary search. I'm just implementing a basic binary search here, and we can think about it in edge cases later. Let's say this is the binary search, left comma right equals to 0 comma length of arr minus 1, and while left, this is just the basic binary search. Calculate the midpoint, which is left plus right minus left by 2. So now the search criteria. So which is the search criteria here would be, so if the ARR mid so let's say target, so this is just a classic binary search, there's not much to explain here, like is equals to mid minus 1, so otherwise return right. I think this should be plus. Minus 1 is left by 2. Yeah, so this should be, you should return a job ID now. We have the binary search. So let's see, is there anything that we're missing? So here I think, let's see if we can try to, should we need to, can we do the binary search on the jobs, or can we do it or on just the end times? Because okay, so because we are already sorting the jobs, if we just do the binary search on the end times, that should also work, I guess. let's say if I just put n times equals to uh, e for e comma in jobs, because the jobs are already sorted, I think this should work. So here I'll put this n times here. Okay, and then now so SEP jobs of ID binary search job ID, skip the profit, top of -1. I think let's try running this. Okay, so there is some edge case that is failing. Hmm. Okay. Okay. So I think I found the issue. So there is a chance that this job ID can be negative, because yeah, let me so x or the job underscore ID not equal to -1 L0 -1. If here I think so, if I think if it's I greater than 0 L0, let's see. Okay, I found the issue. So since we are our DP is 0, the jobs is 0 indexed, while the DP is single indexed. Like it's so the job 0 represents an actual job, but the DP 0 represents does not represent, so it should be +1 here. Okay. Okay, so thank you. Let me know what you think about this approach and the other two approaches. Thank you.